Okay, so this is the live synchronous session for module 6, session number 1. So there'll be 2 other sessions on these topics later in the week, Friday and Saturday. All of them will be recorded, so you can always find those recordings. You should have a link in your course homepage, or you've gotten emails about it that take you to the schedule that tells what's going to be covered, and also has the links for the recordings as well as the actual Zoom meetings. I am talking right now, so hopefully those of you here can hear me, or you're reading what's on the screen and following the instructions if you can't hear me. And hopefully that is long enough for that to be figured out if it needed to be. So as always with these, you can participate using the chat or using reactions. If you want to raise your hand, if you want to actually ask a question, that can be helpful to let me know so you don't have to just interrupt. But if there's a pause, you can certainly just turn on your microphone and talk as well. So feel free to do that. I have plans of what to go over from module 6A and 6B both. But if you have specific questions you want to look at, you can ask those as well. So we'll come back to this later with the feedback. So there's the link that you'll use at the end of the session just to let us know that you attended and how it went. But I'm going to go ahead then on to my content. So we're looking at composition of functions and inverse functions and exponential and logarithmic functions. 6A is the composition and inverse functions. So this is kind of follows up with what you did at the beginning of chapter 3 of learning function notation, and you had the ways of combining functions, right? So you had like f plus g, or it could be written like this, f plus g of x, and that meant f of x plus g of x. And you had f minus g, same deal, could be written with the parentheses in the x. Either way, that meant you took f of x minus g of x, and you had the same thing with times being multiplying the functions, and division. So in section 6.1, you get a new notation, and it uses an open circle. So it's not the same thing as the multiplication. That's just the dot. This is f circle g. This is read f of g. It can be written with the parentheses. But what that is rather than doing stuff with the functions separately and then combining them, you do them one at a time. So you first plug in to g, and then you get that result, and you plug into f. Or if it was g circle f, you would first plug into f and then into g. But this is what you want to, whenever you see this with the circle, first thing you want to do is rewrite it as f of g of x with the g of x inside of the f of x. Okay, so that's the notation. And I'm going to look at some questions, and I'm just going to write this up here. So f circle g of x, always the thing to do with that is that's f of g of x. All right, so I'm going to start with homework problem number 2. So this is evaluating from a table, doing the composition. So I'll just take these one at a time, and let me get zoomed in here so this shows up a little bit better. So starting with, we have f circle g and then the 1, and that means f of g of 1. So I start and I work my way from the inside out. G of 1 means what is the y value for g when x is 1, or with this table of values, it's really, so we're looking for x is 1, what is g of x? So we look at the x row, we find 1, and go, and we get the g of x is 0. So g of 1 is 0 from the table of values. Then I can replace g of 1 with 0. And now I'm looking for f of 0. So now 0 is my x value, but I'm looking for what's the f. So if x equals 0, what is f of x? And so I find 0 on the x, and I look at f of x, and it's -1. And so that's going to be my answer. So you just have to take it one step at a time. It's going to have that 2 levels of process. F of g of -1. So f of g of -1, starting with the g of -1. So -1 is x. Then what's g of x? So I find the -1 in the x row, find the g of x that corresponds to that, and that's 0. So now I replace g of -1 with 0. So now I'm looking for f of 0. And then, so I find 0 in the x row and find the f, and that's -1. All right, then g of f of -1. So now I'm starting with f of -1. So looking for an x value of -1 and finding the f of x. So x -1, f of x is -3. So I replace, so this means f of -1 equals -3. So I replace f of -1 with -3. And I'm looking for g of -3. So for x equal -3, what is g of x? And so I find the -3, and I look at the g, and it's 8. Okay. So hopefully you kind of get the idea, but I'm just going to keep, I'll go and do the other 3 here. So g of f of 0, again, I always just rewrite it in the sort of nested notation. So I start with 0 on the x. I find f of 0 is -1. So that becomes g of -1. And then I look up -1 and find the g, which is 0. And then we have g of -2. So I start with -2 is the x value, and I find the g, and that's 3. Now I'm looking for, if x is 3, then again, what's g of x? So that g of x value becomes the next x, but still looking at g of x, so then that would be 8. So I think that's enough. I wanted to get to one that had the same function, but similar process for the other one. So then the next question I want to look at is number 3, which is evaluating compositions from a graph. So it's going to be a similar process, but instead of having the table of values, you have the graph. So like g, again, just the notation, I rewrite this as g of f of -1. And so I'm looking for the point for f of -1. I want on the f graph, I'm looking for a point that has -1 as the x value, and I want to know what's the y value. So I look on the f graph, which is this sort of check mark shaped one. I find -1 for the x coordinate, and that's this point here with +1 for the y coordinate. So that means f of -1 equals 1. I replace f of -1 with the 1, and now I'm looking for g of 1. So now I'm looking for 1 on the x, and I'm looking for where that intersects with the g graph, which is at 6. So that's going to be g of 1. So again, you just have to take it one step at a time, do the whatever one comes first. So you're kind of switching orders. You're starting with the 0 or with whatever's in the parentheses, the number that's the X value, and you're working your way from right to left as far as, so 0 for the X, find where that is on F, then take that result as the X and find where it is on G. But that would be the process with the graph. I'm not going to take time to do more of those, but just to see kind of how that step-by-step process works. But you can't do it just in one step. You can't just look at the graphs and the -1 and immediately just see G of F of -1. Do it one step at a time. So then I want to look at number 4, which is just doing where you're given the equations. So looking at F circle G of 4, so this is F of G of 4, and so I'm starting with from the inside out. So starting with G of 4, G of anything is 4 times that thing squared plus 3. What I'm plugging in there is 4. So this is 4 times 16 plus 3, which is 64 plus 3, which is 67. So now I can replace G of 4 equals 67. So I replace F of G of 4 becomes F of 67, but F of anything is 9 times that, and 9 times 67 is 603, I think. Grab a calculator. Yeah, 603. So that would be the process there. Again, write it out as the nested function notation, work your way from the inside out, plugging in the number into the inside function first, get that result, plug that result into the outside function. All right, so then the next thing I want to look at is number 7. And I'm just going to look at some parts of this, but this is finding the composite function. So we're not now plugging a number in, we're just finding the function and the domain. So the domain of a composite function, you have to look at excluding anything that couldn't go into the inside function, even if it could go into the result of the combination. So let me just do this example. So F of G of X. Here I don't have anything to plug in for X, but I'm going to replace G of X with its equation. So we're looking for F of -5 over X. But F of anything is taking that thing over that thing minus 8. So when I plug in -5 over X, I'm plugging that in those places. Now for the domain, because I have to plug into G of X first, X can't be 0 because that couldn't go into G of X, right? When we have anything on the denominator can't be 0. But then when I actually simplify this, so I have -5 over X, and then I can, I think I'll just multiply everything. So I'm going to multiply the top by X and the bottom by X to simplify this. So I get -5 over -5 minus 8x, and I can make that all positive. So 5 over 5 plus 8x, something like that. And now I could plug in 0, but that still has to be excluded from the domain because we're plugging into G first. But what I can't plug in now also is anything that would make the 5 plus 8x equals 0, which would be -5/8. So X also can't equal -5/8. Now that could be found also by looking at what value of G. Did I do this? Value of G is going to. Yeah, okay, so what value of G is going to make come out equaling 8, because for f of x, x can't equal 8, but we're plugging into G of x first, so we'd have to figure out that negative 5/8 would also be the solution of g of x equal to 8. But it's easier, I think, to just go ahead and find, so throw out anything that would make the first function, the inside function, 0 or denominator 0, but then also throw out anything that would have to be excluded from the domain of the final result. So the actual composite function, 5/5 plus 8x, and then I think it'll ask the domain. Yeah, so the domain is going to be x not equal to 0 and negative 5/8. So you could do that same process with g of f, switching it around, which is getting plugged into which, f of f, g of g, but it's going to be a similar process on those. Then I also wanted to look at number 8 a little bit, where we're doing the same thing, but now we have a radical. So the rules you have for domain in these sections, same that we had in chapter 3, but so we can't have denominator equal to 0, and whatever's inside the radical has to be greater than or equal to 0. But again, when we have the composition, we need to eliminate anything that couldn't go into the inside function, and then also, you know, what would work in the combined function. So if I have f of g of x here, that's going to be, so f of g of x, f of anything is square root of that, but what we're plugging in here is g of x, which is 8x plus 7. So square root of 8x plus 7. Now, g of x, the domain, is all real numbers. So nothing would have to be excluded from g of x, but once I plug it into f of x, now I need that 8x plus 7 to be greater than or equal to 0. So ends up being x greater than or equal to negative 7/8. So square root, I gotta do backslash sqrt if I want to type that in, 8x plus 7. And then for the domain, again, in inequality notation, x greater than or equal to negative 7/8. And then looking at the other direction, g of f of x. So g of anything is 8 times that thing plus 7. And then f of x, which I'm plugging in, is square root of x. So we have 8 times square root of x plus 7. Now, square root of x, domain for that, x has to be greater than or equal to 0. And then once we've plugged it into g of x, it's still the same deal. So g of x doesn't add any further restrictions, but we still need x to be greater than or equal to 0 for that square root to work. So so that's finding the composition of functions and their domain. And that's pretty much what I had for composition. And we're moving on then to inverse functions. So I want to talk a little bit in general about inverse functions first, and then we'll look at some examples. So we have our function where we have f of x equals y, or you might see it as y equals f of x. So the first thing is the notation. If I say f inverse of x, so it's with a negative, looks like a -1 power, but it's a new different way of using that -1 power. So it's not the same as if I have like x to the -1 power. It's a completely different thing. So what does f inverse mean? What is the inverse function? There's two different ways to think about it. One is it's going to switch x and y. So if f of x equals y, then f inverse of y equals x. So if I have any particular values there, if I have f of 1 equals 7, then that means f inverse of 7 equals 1. If I have a 0.23 on the graph of f, then the graph of f inverse will have the 0.32. The domain of f, we switch x and y. So domain is x's, it's going to switch to the y, so that's going to be the range of f inverse. Similarly, the range of f is the domain of f inverse. And these go both ways because if like f is the inverse of f inverse, so it's like opposites. -2 is the opposite of 2, 2 is the opposite of -2, whichever way you think about it. So this allows us, so far you haven't really been asked to find the range from an equation, but now what we can do is if you can find the inverse function, you can find the domain of that, that's going to be the range of the original function. The graphs then, if we think about what happens with the graph, if I have my function doing its thing and it has its points, if we switch the x and y value of those points, that's going to basically reflect them over the line y equals x. And I've limited time, so there's kind of a method that if you think of, here's the x-axis and here's the y-axis, if you think of switching those physically, that's going to split that graph over that line. So one thing that means is the graphs of a function and its inverse, if you plot them together, they will intersect if they have intersections, those intersections will be on that line y equals x. Because they could have other intersections. But if one of them crosses the line y equals x, the other one also will at the same place, put it that way. So that can help you identify, especially on the homework, sometimes you'll be looking at, multiple choice, which is the graph of the function and its inverse. And any that don't have those intersections on the line y equals x, if they're intersecting elsewhere, then those are probably not the right ones. So to find the inverse function, what you can do is you switch x and y and then solve for y. Or you can think of it as you're solving for x and then switching x and y. So that's one way to think of inverses. The second way to think of inverses is, and I'm kind of not giving myself a lot of room, but the inverse function is the undoer. So if you think of the function as taking an x and it starts wrapping it up in layers of operations, maybe it squares it and then adds 5 and then whatever. So each operation that happens to x is a layer of wrapping. What the inverse function does is it starts at that outside layer, unwraps it until it gets back to the x. So it's the reverse operations in reverse order. This is where you also see if you do composition, if you do f inverse of f of x, so you put an x into f, you get out of this result, you put that result into f inverse, it'll give you back the x you started with, and the same way in the other direction. So you can test whether two functions are inverses by plugging one into the other and see if it comes out x. If one does, the other should also, but I think the homework will have you test both directions. And then, so to find the inverse function, then sort of the second possible method is, as long as there's only one x showing up anywhere, you list what happens to x, and then you do the reverse operations in reverse order. So that's kind of two ways to find the inverse function, and I'll look at both of those. So all right. I'm going to do some examples, but I want to keep some of this up. Okay. All right, so continuing in this homework section, I want to look at number 28. So here we have a function. We're going to find the inverse of the function. We're going to find the domain and the range of the function and its inverse. And we're going to, in this case, multiple choice, choose the correct graph that has the function and its inverse. All right, so finding the inverse two ways. So method one. So method one is the way you're going to have to use if x shows up more than one time, then you couldn't use method two. But method one is we switch x and y. So you have to know, first of all, that f of x is y. So this is y equals x cubed plus 1. To find the inverse, I switch it. And so it's x equals y cubed plus 1. That's already the inverse, but it's not in function form. So I want to solve for y. So subtract 1 from both sides. Y cubed equals x minus 1. Then cube root to undo the cube. And we get y equals cube root of x minus 1. Method 2, it's going to come out the exact same way, but we just think about it a little bit differently. So I'm going to list the things done to x in the x cubed plus 1. So the first thing that gets done to x is a cube. The second thing, after you cube it, you add 1. So I'm going to undo those in reverse order. So I label these. So I'm going to do step -2. So undoing step 2, subtract 1. And then undoing step 1, cube root to undo the cube. So I just look at that. So I have x minus 1, and then I apply the cube root onto the x minus 1. So you can do either of those, other than, again, if x shows up more than one place, you can't really do method 2. So we have this, this is cube root of x minus 1. Okay, so then to find the domain and range, so we're finding the domain and range of the function and its inverse. Now, here's a shortcut. This is a cube, right? The cube function, the domain and range are all real numbers. So the inverse is going to be all real numbers. Nothing going on here with the domains. It's all real numbers. When you get to some of the other ones, and I'll do an example that's irrational where it matters. But in this case, all real numbers for the domain of f, all real numbers for the range of f, etc. So I'm not even going to bother doing the rest, but domain and range of f inverse would be the same. All right, so then I want to look at number 33, which is going to be kind of similar. Did we get there? That's 31. Okay. So similar process here. We're finding the inverse, finding the domain range. Oh, you know what I did want to do with that previous one was look at the graph. So I guess I do need to do the rest of the domains. All right. Okay, so here's the graph. So we're looking at graphs where they intersect. So one thing to be aware, you can pop out these graphs to look closer at them. But notice here, this graph, it's crossing the line y equals x and not at the same place. So that one's no good. And same thing on this one, we have each of those graphs intersecting this dotted line, this y equals x, and not at the same place they intersect each other. Same thing on C. So again, that's enough to immediately tell this is not the graph of the function and its inverse. But if you look at D here, where each of them crosses that line is also where they intersect each other. And you see that that's the line of reflection. That's the mirror that they're reflecting over. That's the correct graph. So that's kind of what you want to watch for on the graphs. You don't even really have to, when it's multiple choice, you don't really have to know how to graph x cubed plus 1 or its inverse. You just have to know where they need to intersect. So, okay, going back then to number 33. All right, so here we have a rational function. So f of x is 2 over 7 plus x, and I'm finding the inverse and the domain and range of each. So I'm going to do, again, both methods. Method 2 is a little bit more complicated with this one, but method 1, I switch x and y. So recognizing the f of x is the y, I'm going to switch and have x equals 2 over 7 plus y and solve that for y. So I'm going to multiply both sides by 7 plus y. And then I have to distribute the x. So I have 7x plus xy equals 2. Then I want to isolate the y term. So subtract 7x from both sides. Xy equals 2 minus 7x. And then I can divide both sides by x. So I get y equals 2 minus 7x over x, or 2 over x minus 7 would be another way to write that. So that would be the inverse function. Now looking at the domain and range, so we have f is 2 over 7 plus x, f inverse is 2 over x minus 7, or 2 minus 7x over x. And we want the domain and range of each. The domain is easy. The domain of f, well, the 7 plus x, that denominator can't be 0, or can't, yeah, so x can't equal -7. That would break. For f inverse, the domain, if I look at that, x can't equal 0 because we have the denominator of just x. For the ranges, so that would be the domain of f inverse. But for the ranges, then we just switch them. So we switch x to y, and we switch. So the range then of f is y can't equal 0. And the range of f inverse is that y can't equal -7. So that's we have there. Move these a little bit out of the way. All right, so the f inverse was, and I think like you could do either way, 2 minus 7x over x accepts that. Or if I go back, well, let me go back. I'm pretty sure it's accept 2 over x minus 7, but not 2 minus 7, or 2 over x, like 2 over x minus 7x. The x has to apply to both. But all right, so the domain of x is not equal to -7. So here it already has the x not equal written in there. Then the range of f, y not equal to 0. I found that by finding the domain of f inverse. The domain of f inverse, x not equal to 0. And the range of f inverse, y not equal to -7. But we have that matching up of the domain of f with the range of f inverse and vice versa. So, all right, I want to look then at that question of, and what if, I wanted to do method 2 also. So if I wanted to find that inverse using method 2 of looking at it as undoing, then if I look at x, what's happening to x? First thing, if I'm plugging in a number for x, the first thing I do is add 7 to it. But then somewhere in there, you have to recognize, well, the x is on the denominator. So once we have the 7 plus x, that's going on the denominator. So I'm going to refer to that as flipping. So we're putting it on the bottom. And then the third thing, multiply by 2. But you can see already this is a little bit more complicated, harder to recognize really what's happening to x. But if I reverse those, then I would divide by 2. And then the way you reverse a flip is by flipping again and then subtracting 7. So here I would get x over 2, but then I would flip that and get 2 over x and then subtract 7. So there's the 2 over x minus 7 from method 2. But then the other thing I wanted to look at also was, what if this is a little bit different? So I'm going to clear this off and say, what if we had f of x equals x over 7 plus x? So now I can't do that method 2 because there's 2 x's. So I can't just say, here's x, here's what you do to it, and list them one by one. So I have to just do the switch x and y. So x equals y over 7 plus y. We multiply both sides by 7 plus y and get 7x plus xy equals y. So then I need to combine and get the y terms on the same side as each other. So I get y minus xy equals 7x. And then factor out the y. So y times 1 minus x equals 7x. And then divide both sides by the 1 minus x. So that's maybe a little bit more complicated process. You have to recognize where you have to distribute and where you have to factor out to get the y isolated. So, okay. So that's inverse functions. I think that's enough for now about those. So I'm going to switch over then to 6b. And again, if you do have questions over anything, specific things you want to look at, feel free to put those in the chat. But section 6b, then we're looking at exponential functions and logarithmic functions. Now, exponential functions should be somewhat familiar to you, to at least know, like, if you have 2 to the 4th power, what does that mean? But now we're having, 2 to the x power. So we're having the variable be in the exponent position. And what we want to look at then, and where the logarithms come in, is what if I want to reverse that? So if I have 2 to the x equals 5, how do I solve for x? And what I would be looking for is, what power of x equal to 5? If I have a function f of x equals 2 to the x, and I want the inverse function, so I'd have y equals 2 to the x, and I would turn that into, switch the x and y, x equals 2 to the y. But to solve for y, you can't divide by 2, you can't divide by y, like this is saying what power. So all I know here is y is the power of 2 that results in x. And so somebody at some point said, well, we're going to call that logarithm. We're going to call it log base 2 of x. Log base 2 of x is the power of 2 that results in x. So that's what logarithms are. They're the inverse of exponents, which means they're the undoers. So the way you undo an exponent is by a log of the same base. If you do composition with them, they undo each other. So like log base 2 of 2 to the power, like just gets that power back, and the other way around as well. And also being the inverse is, the x and the y switch. So you have all those characteristics with the graphs and the domain and range and how they relate. So, all right. So your sort of first basic introduction then is if something like if a to the x equals y, that's the same thing as log base a of x equals y. So notice the base is the base, and then the x and the y kind of switch positions. But you don't want to think of this as a, like x as being a power in the a. You want to think of this as log of x, and then a is kind of the base down below. And then we have some special bases. So base 10, we don't write, we just write log of x. So log of x equals y is equivalent to 10 to the y. I'm sorry, I didn't switch these. Let me, all right. A to the x equals y would mean log base a, but the x and the y actually switch. So, but yeah, so if it's 10 to the x equals y, that would be, it would be log base 10, but you don't write the base. Log of y equals x. And really, yeah, it's not about the x or the y or the a, it's about the positions. So I could do it 10 to the square equals triangle, then that would mean log of triangle equals square. It's about where those are positioned, not whether it's x's or y's or a's or b's. But then we also have e. So e to the x equals y corresponds to what we call the natural log, but it was made up by somebody who used Latin, and so is like, you know, logarithmus naturalis or something. Anyhow, so they abbreviate it ln. So ln of y would equal x. So you'll see all of those. But I'm getting a little ahead of myself. So first I want to talk first after all this. But just basically the graphs. Exponential, the graph starts out flat, it gets steeper and steeper. So it has, it flattens out along the x-axis. So it has a horizontal asymptote at y equals 0. It kind of has its biggest turning point right around, like close to the origin. But then if you like, it doesn't actually flatten out to a vertical line, but just it gets really steep. So so it almost looks like it goes vertical, but it does keep going forever to the right and up. It doesn't have an asymptote in the other direction. Then for the logarithm, that's going to flip. And so it has a vertical asymptote and then a turning point around the origin and then flattens out, but is still going up forever and sideways, where the downward arrow is just downwards, not sideways. So it has a vertical asymptote at x equals 0. So notice the x and the y switch, vertical and horizontal switch. We have, you know, those intercepts kind of switching from the y-axis to the x-axis. But you want to get that general shape for the exponent. It's like a horizontal line and then a curve. So it could be going different ways, but the important thing is like it has that sort of horizontal looking piece. Whereas the logarithm has the vertical looking piece and then the curve, whatever way it happens to be going. So you'll have a lot of multiple choice graphs on these. So that's what you kind of want to watch for. And then the turning point, that's what you want to look for to figure out, has it shifted up, down, left, right? Well, the asymptote will be part of that, and the location of the turning point will be the other part of recognizing those shifts. The domain for exponents, the domain is all real numbers. The range, if it hasn't been shifted, it would be 0 to infinity. So everything above that horizontal asymptote. If it gets flipped, of course, then that would change. And then for the vertical, or for the logarithm, it switches. So the range then, or the domain, would go from 0 to infinity. And the range would go all real numbers. But generally, like the endpoint of the domain for the logarithm is going to be, you know, wherever the vertical asymptote is, those are going to match up, and those are going to correspond to, so we now have a new domain rule, which is whatever's inside of the logarithm has to be greater than 0, not greater than or equal to like the radical, but strictly greater than 0. Doesn't matter what's outside the logarithm, that has no effect on the domain, just what's inside the logarithm has to be positive. Okay, so I'm going to look at a couple graphing tools to start with. So looking at number 9. So we have this graph, and I'm starting with the graph of e to the x and using transformation. So I click the graph, and I'm choosing the exponential tool. So when I click on this, it says down here that I've selected the exponential tool. So if you're not sure, and you know it's exponential, you want to make sure you've chosen the exponential tool. It just says click the graph. I can click literally anywhere on the graph and it'll give me this starting point. So then I need to look and make sure. So my equation here was 15 minus e to the negative x. So the first thing you want to check for is the base. So that's down here. So I want to make sure the base, I have a base e and it's e. And then you want to kind of work your way from the x out and think of, all right, the first thing that happens, the x, it switched to negative x. So that's a reflection. That's a horizontal reflection, to a reflection over the y-axis. So we see that flip happen. Then, so we have e to the negative x, but then it's negative e to the negative x. So it's been reflected also over the x-axis. And you see that flip on the graph when I click that. And then we have the 15, and you can think of this instead of as negative e to the negative x plus 15. So that's a 15 added on outside, so it's not like with the x. So this is a vertical shift by 15 up. So that's kind of the process you want to go through of everything that makes this function different from the beginning graph of e to the x has to do something in one of these tools. Now this one it already gave and started with the correct base. The next tool I'm going to show you, you have to put in the base. So you have to watch for that. But yeah, so that's looking at this then. So the domain of any exponential function is always going to be all real numbers. So you don't have to, and if you try and look at the graph, you might think, well, it looks like it doesn't go all the way, but it does. So you just have to know that. For the range, though, you can see where it flattens out here. That's the 15. So it would be at 0, but it's 15 that it's been shifted up to, and it's everything below that. So the graph is helpful there in figuring out what happened to that base range. That would be 0 to 15, but now it's going from, or it would be 0 to infinity. It's flipped, so it's going from negative infinity, and then it's shifted up to 15 instead of 0. And then the horizontal asymptote is always going to match up. So for the exponential, horizontal asymptote matches up with the endpoint of the range. For the vertical, or for the log, the vertical asymptote lines up with the endpoint of the domain. So I want to jump then to number 43, which is going to also be using a graphing tool. So this one, we're graphing the function and its inverse. But notice the only thing here is just the base, 9 to the x, and then log base 9 of x. So I'm going to graph both. So if you look here, this is the exponent, this is the logarithm tool that has, starts out vertical and flattens out. And then the exponent tool starts out horizontal and curves. These aren't super good little pictures where, like, yeah, if the exponential tool got flipped, so you just have to look at those names and look at, understanding this is the basic, unflipped or unmoved. So the exponential, I click anywhere, and all I need to do is say this is base 9. But in this case, it's not starting out with the right base. I have to change the base, but nothing else has been done to this to shift it, reflect it, stretch it, anything. So just base 9, and there it is. And then the logarithm, same deal, click anywhere, put in the base. And notice when I change that base, as I do a bigger and bigger base, it doesn't really, but like if it was base 2, then you'd have a less sort of steep graph, a less tight curve. So the larger the base, that's going to make that graph get flatter more quickly and have a sharper curve where it curves. But you can see those two graphs then, have that reflection over the line y equals x, even though that line isn't drawn. But that's that one. Okay, looking more then at the asymptotes, turning point, the domain range, I want to look at a logarithm one, so looking at number 46. So we have 1/2 log of 2x. The domain, all I need is the 2x to be greater than 0. And so that means x is greater than 0. And it wants interval notation, so that's going to be going with parentheses from 0 to infinity. So then I'm choosing the graph. So again, the logarithm is going to have a vertical piece, not a horizontal piece. So that means that, this is no good. This straight line, of course, is no good. I want a vertical piece. And then if I look at this, all that's happened is I've applied some vertical and horizontal stretches and reflections. So there's no shifts that have happened. There's no flips that have happened. So it's going to be the vertical piece going down and then the curve happening close to the origin. So that's option C here. And again, you can click on these graphs to get a little more detail. But so B and C, you have to then be aware again that the logarithm, they look pretty similar, but the logarithm has that piece that looks like it's completely vertical versus the exponential having the piece that looks completely horizontal. So then it asks for the range, and so the range is going to be for the logarithm automatically always all real numbers. So infinity, negative \INF to get infinity. And then the asymptotes, so that's going to be that vertical line for the logarithm vertical, and it's going to be x equals the x, that first part of the domain. So 0 there. And then it says find the inverse. So I have to do some work to find the inverse here. So I can do either method. So method 1 is I would write x equals 1/2 log of 2y and solve for y. So I'd have to use the fact that if something to a power equals a thing, then that means we have log base of the base and then switching the other two. So I could rewrite this, but I would need to get the log. So I don't want to have anything in front of the log. So 2x equals log of 2y. Then I can look at this. Base isn't written. So this is base 10 when it's not written. So this would be rewritten as 10 to the 2x equals 2y. And so then y equals 1/2 times 10 to the 2x. The other method, if I list the things happening to x, the first one is multiplying by 2. The second one is log base 10. And the third thing is times 1/2. So when I reverse those, I have a times 2 or divided by 1/2. So there's the 2x. And then the next step, undoing the base 10 log, is base 10 exponent. And then undoing the times 2 is times 1/2 or divided by 2. So either way, getting the same result. So you can kind of pick whichever one you like best. This is times 10 to the 2x. All right, and I just used asterisk to get that multiplication in there. And then the domain, we already have the domain and range of f, so the domain and range of inverse are just the opposite. So the domain in this case is all real numbers for the exponent, and then the range is going to be from 0 to infinity. Right, and then choosing the graph, we want an exponential graph first off, so it needs to have not a straight line. We got to have that like horizontal piece, which a couple of these do. This one doesn't really look like, it doesn't have a horizontal or vertical piece. All right, so now I have to do a little bit of work. These are really similar looking graphs here. This one looks like it's crossing the axis at 1/2. And so it's a little bit shallower. This one is crossing the y-axis at 1. So that's the main difference I see, and I can really calculate. So I can look and say, all right, if I plug in 0 for x into this, I would get 10 to the 0, which would be 1 times 1/2. So I need the one that's crossing the y-axis at 1/2, not at 1. And you can see kind of the squareness of it, kind of that corner matches up with the graph that we chose for the logarithm as well. So, all right. Moving on from the graph then, you want to be able to do logarithms and exponents in your calculator. So just real quick, if you're on like a standard like TI graphing calculator, you have the log and the ln here, and you have the e to the x as the second on the ln. Notice there it's ln, it's not in. So sometimes people try to type ln into MATLAB with a capital I instead of a lowercase l. So make sure that you're doing that correctly. It will come up, the MATLAB is going to be like, I have no idea what you're talking about if you do it with a capital I, because that's not correct. Then if you're on like a TI scientific calculator, you have the log and the ln and the e to the x again as the second on the log. And then if you're on the Casio scientific calculator, you have the log and the ln and the e to the x. And you even have an any base log, so you aren't stuck with just log and ln on that, and kind of on the right hand side instead of the left side. But yeah, so make sure you, whatever calculator you're using, if you're using the computer calculator, you have to do things kind of in reverse order, even when you have the log and the ln. If I try to type log of something, I have to actually put in the thing that I'm taking the log of and then click the log button for it to calculate. And same thing with the e to the x. So if I do the second and I want to do the e to the x, I have to put in the number that I want to do e to the x of, and then if I want to do e to the third, I have to put in the 3 first and then do e to the x, and it'll do that. So not quite as nice to do as what you'd have on those scientific or graphing like handheld calculators. I want to also point out on the formula sheet, you have a lot of properties of logs, what you'll be doing in section 6.4 and 6.5, or sorry, 6.5 and 6.6, particularly 6.5, but then you'll be using them in 6.6. So those are here, but what's not on here is what I've talked about so far, that relationship of, you know, log base b of x equals y corresponding to b to the y equals x. That isn't on there. Another thing that's not on there is the properties of exponents. So it's assumed that you already know those, what you do if, you know, a to the m times a to the n is a to the m plus n. A to the m to the nth power is a to the m times n. All of those things, nth root of a to the m is a to the m over n. All of those, so you may need to review those, or will need if they're not, if you're not comfortable with those, you'll need to go back and refresh on those as you're doing this. All right, so back to the homework. I'm going to look at number 21. So this is just, that's not the one I want. Oh, that's 6A. All right. 6B, number 21. So just doing a calculation. So if I'm plugging in 5 hours into this, so H represents, says the number of hours. So I'm plugging in 5 for H. So I need to calculate 8e to the negative 0.19 times 5. So you need to be able to do that on my computer calculator, which is all I can really demonstrate to you. I would have to put in, if I do it all at once, I'd have to do 8 times, and then I would put in parentheses the 0.19 and make that negative, and then times 5, close parentheses, and then I would do the second e to the x to put that. So I could do it that way. It does also have just an e button, so I think I could do e to the power of, and then do the negative, negative 0.19 times 5, and then multiply that by 8. But just figure out whatever calculator you're on, make sure that you can do those calculations involving e as the base of the exponent, and then make sure you follow the rounding instructions on those. And then number 42 is just using the natural log. So just make sure you know the ln button to use, and you put that in. So yeah, I'm not actually going to do that. But looking at then the exponent and log relationships, just well, yeah, I think I won't do those because I'm out of time. So if you want to see more of those, come to the Friday and or Saturday session. That's just a matter of paying attention to the instructions of what's being asked for and using that property, a lot of using that property of the exponential converting to the logarithm, or the logarithm converting to the exponential, using the properties of exponents. So that's pretty much what's going on in the rest of this. So any questions from any of you before I end this? I'll go ahead and go. So you have this link with the survey. So that'll stay open, I think, through Sunday night. So if you're watching the recording, you can still use that if it's before whatever that is, the 2nd or 3rd or whatever October already. But yeah, so I'm going to go ahead and stop the recording. So if those of you in the room do have questions that you just don't want on the recording, I'll stay a minute to see.